Right, so at the end of last time, I was telling you, but not terribly explicitly, I was telling you how to solve question 2 from exercise sheet 1. Okay, by staring at a suitable diagram and seeing what happens. Okay, and so we ended up with something which was constructed from the de Rham complex. So here's the usual de Rham complex. Right, except that this is on a contact manifold. It means that there's a line subbundle inside here, and so on. Okay, then it turned out there was a second order differential operator which gave you the conditions to be in the range of this one. Okay. Actually, if you look at my notes in the Dropbox, they're all over the place, but perhaps the exercises are better organized. So, and I'll just say the first exercise sheet really was heading towards this in question 2. In question 3, it was a very similar sort of thing in 2 variables rather than 3 variables. And you're asked to think about what's happening in 2 variables with very, very similar operators. And actually, this is to think about 2 variables in terms of 3 variables. That is a very standard technique, especially in mathematical physics, whereby you're thinking about dimensional reduction. So you have some equations that you're interested in, and you want to study them under a certain symmetry, and you'll get a system in fewer variables. So that deals with what's really going on in the first exercise sheet. The second exercise sheet has only 2 questions. One of them is to compute the curvature of the round metric on the sphere, whatever that means. Okay, so at this point you have to look at some literature or some books on differential geometry, especially Riemannian differential geometry, and you will find that the formula for the round metric on the sphere, I've lost the ability to write. You'll find that the formula for the metric, the formula for the curvature on the round sphere is a very simple looking formula in terms of the metric itself. Okay, and that is actually important in what I'm about to do next. And then the rest of the questions are sort of variations on this theme. There's an algebraic question on the second question sheet, which is to do with this diagram chasing, which we're going to do to create the Saint-Venant complex in R3. And on the last question sheet, I get a bit carried away. All right, and I'll tell you what's going on. All right, so we'll go back to this Saint-Venant complex. Okay, so back to Saint-Venant. Okay, so the Saint-Venant complex was something which was only on R3 with its flat metric. And what happened is that you found that this sort of thing was controlled by something called a connection. So you have a connection, the formula for which, if you have curvature as well, if you're on a general Riemannian or even pseudo-Riemannian manifold, the formula looks like this. So this is what happens if you take the Killing equation and prolong it. So you get this minus mu bc. So mu is supposed to be skew. So that the first equation here is recording the fact that the symmetric part is 0. That's recording the Killing operator. And then these sorts of things that I'm writing down here are actually just differential consequences of mu being defined in this way. Okay, and in the flat case, this turned out to be 0. In the curved case, what you get is this. Okay, so there's an extra curvature piece just being added in. Okay, now, okay, so in the flat case, it's not too surprising that when you compute the curvature of this connection, this bigger connection, you get 0. After all, you started with flat space. So on R3, that's what happens. So perhaps you could try something a bit more exciting as a manifold, like the sphere, the three-dimensional sphere, or even the n-sphere, doesn't matter what dimension it is, and just see what happens. Okay, so first of all, in general, if you work out what the curvature looks like, so what I mean is you just formally do this differentiate twice and then take the skew part over A and B, you'll find that what you get applied to this gadget. The formula, at least, is relatively simple, and it sort of indicates that there's something going on above and beyond flat space. In the first slot here, you just get 0. That's really good. All the sort of curvature shows up in the part down here, and what you get is actually exactly this formula. You get something involving the curvature and mu, and it's this. You get A, B, E. Actually, you get 2 of these, 2 lots, C, mu, D, E. Right, so this is something which is skew in A and B, skew in C and D. This is the skew part, plus the same thing. So this is just some mindless computation. I'm a great fan of mindless computation, by the way. So this is the same thing with A and B interchanged with C and D. That makes it symmetric in A and B. And then you get another term, and it's minus. And now you get the derivative of curvature. This is the covariant derivative of curvature. That's how sigma feeds in. Okay, so you see that the formula is actually relatively simple. And on flat space, you see that this derivative of curvature is 0. And here I just have to warn you about a convention in mathematics to do with differential geometry. Any Riemannian manifold whose curvature looks like this, perhaps with a constant in front of here, is called constant curvature. Whereas I thought, when you first heard this terminology, that constant curvature would mean constant curvature, right? It should mean that this is equal to 0. But that's not true. Okay, it's all to do with one of the classical people. I think I can chase it back to which particular classical person. But anyway, this is called constant curvature, whereas here, if you want this derivative to vanish, this is a stronger condition. So A, B, C, D equals 0. What people say, if that happens, is your manifold is locally symmetric. And it turns out that locally symmetric manifolds really are locally symmetric. In other words, if you look at the infinitesimal automorphisms of such a manifold subject to this, right, there are heaps of them, quite a lot of them. Okay, so locally symmetric is a good terminology, but if you're viewing it this way, it's perhaps a poor terminology. Anyway, the sphere is locally symmetric, as you might imagine, right? Because if I differentiate this, right, one of the characterizing properties of the Levi-Civita connection is it kills the metric, so it kills the right-hand side. So this is true, for example, for the sphere. In any dimension. But the sphere is not all there is. So if you're going to insist that the curvature looks like that, there's not much choice. You get the sphere, hyperbolic space, or flat space, basically. If you want a manifold which is sort of almost as symmetric as the sphere, but not quite, one of these locally symmetric manifolds, there are plenty more choices. And these things have been classified in the first instance by Elie Cartan. But, and if you look at the classification list, it's very daunting, right? It's a big list like this. Lots of Lie groups involved and so on and so forth. But I can tell you that everybody's next favourite example of a nice symmetric manifold beyond the sphere is the even-dimensional real manifold CPN. Right, so I claim that CPN is the next most symmetrical Riemannian manifold you can think of. For example, when n is equal to 1, it's the Riemann sphere. So the next most exotic thing you can think of is actually starts at CP2. Right. Anyway, the point of me telling you about this computation here is that actually, if you plug in this so-called constant curvature metric, you find actually that not only this vanishes, but actually this combination, this is algebra, this combination also vanishes. So surprisingly, this connection, which you were thinking of should be flat in the flat case and otherwise it wouldn't be, it's actually flat on the sphere. It's flat on the sphere. Oh, by the way, this is lecture 5, isn't it? Okay, just so you don't get worried. Okay, so this connection is flat on the sphere. So actually, you can go through exactly the same diagram chase that you used to create this very lovely complex in flat space, and you can do it on the sphere, and it works just as well. And this is called the Calabi complex. Right, so when you do it on the sphere, or any other locally symmetric space, like, or any other, constant curvature, like hyperbolic space or whatever, you get something called the Calabi complex. Right, so you get an explicit second-order differential operator which characterizes the, the range of the Killing operator. And you can, and now your next question should be, what happens on CPN? Right, so I will tell you what happens on CPN, but first of all, I have to tell you how you should think of CPN as a Riemannian manifold. Right, so it's easy enough to think of the sphere as a Riemannian manifold. The sphere, let's say here's an odd-dimensional sphere sitting inside R2n plus 2. Well, you can think of an odd, this, for example, odd-dimensional sphere. It's a nice round thing. And the metric on here is just simply obtained by taking a flat metric here and just pulling it back to that. Right, and there are some, before I go on, let me just say there are some really lovely ways of viewing the sphere. Not necessarily an odd-dimensional sphere, so say even the two-sphere. Right, one of the exercises in sheet 2 is to check that this is true. And in the notes, I give you a formula for how you compute this thing in terms of a metric in local coordinates. And at some stage, it's very good for your soul to actually do this. Right? And it's really quite hard. Right? There are tricks for getting around it, but at some stage, it's really good to actually just write down in local coordinates what the metric on the sphere is and compute its curvature, just to make sure that you can check this. In fact, this is exactly what happens for the unit sphere. My conventions here are for the unit sphere. So, how would you do this? Let me mention two really good coordinate systems on the sphere, which will help you. One of them is so-called stereographic projection. Of course, if you're going to make a map of the sphere, you've got to get rid of some points because just topologically you can't do it if you don't do that. But let's just remove one point. Let's say the North Pole. Okay, and here's the sphere down there. So one really good coordinate system on the sphere is obtained by stereographic projection. What you do is you have a light source at the North Pole, you just shine it down onto the plane like that, and every point here gives rise to a unique point on the plane. So one of the exercises in the later question sheets is actually to write down a formula for this. So here perhaps you have coordinates, I think, u and v in the exercise sheet. And what I ask you to do is first of all write down this thing as an explicit formula. You know, uv goes to something. Right, it's in the exercise sheet. I won't bother repeating it here. And in terms of that, you could then work out what the metric looks like. And something very, very astounding happens when you do this. When you work out what the metric looks like, it's not too far from being the flat metric in these coordinates. This would be the flat metric in these coordinates. It would just mean that in these coordinates it's just the identity matrix. But this one here is actually a, I think it's 1 plus u squared plus v squared all squared times that. So it's a smooth, non-vanishing function times the flat metric like that, which actually means geometrically that you can measure angles using this metric. Right? So in other words, this mapping from the sphere minus 1 point to the plane is conformal. Right? It preserves angles. Of course, distances are badly messed up when you do this. You know, the next thing you might do, and this is what, in effect, what Mercator did a long time ago, is you might try and unwrap the plane to something a bit more sensible to get rid of this. Anyway, so you can carry it in your pocket. And that was done by Mercator. So if you compose this projection, stereographic projection, effectively with logarithm, this was before Napier even invented logarithms, then you get the Mercator projection, which is conformal, extremely useful for navigation. Right, that's about, I don't know, 1560 something for Mercator projection. So here's one way you might actually compute the metric on the sphere and its curvature. Here's another way, and this one is actually more relevant to what's going on in this Calabi complex. The other thing you might do in order to try and find a really nice metric on the sphere is to put a light source at the center of the sphere. So here is your sphere. We want to make a map of it. Let's suppose we're just content with making a map of the southern hemisphere. And you put a light source at the center of the sphere, like this. Okay, so rather than at the North Pole. And then for each point in the southern hemisphere, you just join it, and you get some point on the plane down here. Right, so, and again, what you're supposed to be able to do is using this coordinate system, you're supposed to be able to write down the round metric on the sphere, and it'll look fairly daunting at that stage. It's in one of the exercises. I've written out what the answer is. And then, even more daunting, you could actually try and work out what the curvature is in terms of these local coordinates. And you'll find that a lot of simplifications occur. Let me just tell you why. So this projection was known to the ancients. So Thales of Miletus, about 2,500 years ago. You know, I don't know where stereographic projection is due to, but you know, the first people to really understand that were, well, just after calculus had been invented and so on. But this one here, that's really a lot better and more ancient. This one here has the property that angles are preserved. This one here has the property that geodesics are preserved. Now, I don't mean geodesics with their preferred length on them. I mean just as curves, right? Because if you've got a curve in the on the sphere, and it's a geodesic, that's exactly a great circle. I'll draw a typical great circle. It looks like that. Right, this is the intersection of the sphere with a plane through it, through the origin. And if you look at what happens to this circle when you project it down onto the plane, you find it's a straight line. That's simply because what you're doing is intersecting this thing with a plane, and that plane is hitting this other plane in a straight line, because planes intersect in lines. Right, so this mapping here has the property that geodesics are preserved. If you wanted a map which enabled you to navigate by always taking the shortest path on the sphere, the map itself would not tell you how long it's going to take to get there because the distances are distorted. But it tells you what to do. It tells you which paths to work on. Okay, and really, the real reason that that this happens, that this connection is flat on the sphere, is that these two metrics, namely the flat metric on the sphere and the the flat metric on the plane and the round metric on the sphere, are so-called projectively equivalent. It means that they have the same geodesics as unparameterized curves. So there's a sort of higher viewpoint going on here whereby this is just sort of, something that you would expect. Right? So this realization is due to another classical person, Beltrami. Right. Anyway, these are how you should. These are good projections to view the sphere. So, what about a good way of looking at complex projective space? For example, just in order to see its metric. Okay, and what would happen when you do that? What would happen to this formula here? So. Okay, so so first of all, what's the metric? Right, so you're taking an odd-dimensional sphere, S 2n plus 1, sitting inside everyday ordinary Euclidean space. But I said that complex projective space was the quotient of one bigger complex space by something. That's how you define it. So I should identify R2n plus 2 with Cn plus 1. Sorry, sitting inside. All right, some choice involved. C n plus 1. Right, there's some structure on here which is being forced on you by thinking of this inside something complex rather than just something real. So this requires a CR structure. Right, but from the point of view of constructing the Fubini-Studi metric, what you want is a metric on CPN. Now CPN used to be the space of lines inside here. So it's this thing up to elements in here which are non-zero up to complex multiplication. But if I normalize them like this, then it's elements in here up to phase. Right, so these elements in here I can think of as perfectly good complex numbers. But if I mod out by z goes to e to the I theta z, right, and then that's exactly what's going on when I'm creating CPN from the sphere. So this is a CR geometry sitting over complex geometry. Anyway, this thing here is, as you might expect, it's an isometry of the sphere. Right, so if you've got on one point on this orbit and another point on the same orbit obtained like that, right, so you've got all these circles sitting inside here. Right, then, well, here you've got a perfectly good metric, and you can identify the tangent space to this with just the orthogonal complement to this orbit, just infinitesimal. It's just the orthogonal complement in the tangent space. Or you could do it at this point. But it doesn't actually matter where you do it because the whole thing, this is an isometry. Right? So because it's an isometry, it makes perfectly good sense to take the metric which is defined here or here, doesn't matter, and think of it as a metric on CPN. Right? So this makes this thing into a Riemannian manifold, and it makes it into a very nicely symmetrical Riemannian manifold. Okay, so this now has a Riemannian metric on it, a Riemannian structure. Right, and it's very, very sort of similar to the sphere. The curvature looks very, very similar. When you're talking about CPN, or more generally a complex manifold which also has a metric on it, Well, in the absence of any relation between these things, that's called a Hermitian manifold. But in the really nice cases, the Hermitian manifold, the relationship between these two things is much tighter. So this thing actually has what's called a Kähler metric on it. And every submanifold has a Kähler metric on it. And strangely enough, this is the relevant, this is the arena in which you do algebraic geometry. And strangely enough, the differential geometry of this thing, differential geometry of Kähler manifolds, is relevant in solving questions which, in the first instance, are actually algebraic. Anyway, when you work out the curvature, what you get is this. So you get the same thing, except I'm going to replace G by a gadget called J plus two lots of G, C, D, right? Okay, so you get some more natural things which are lying around on your manifold, just incorporated into the curvature. So you get what you had before, easy enough to understand. This thing here is, well, if you have the index up like this, which you can view it like this because it's a Riemannian manifold, you're allowed to raise an index here. This is an endomorphism. This is the complex structure. It's why I've called it J. If you have the index down, then people tend to give this a different name, and it's called the Kähler form. So the Kähler form is the natural gadget that you have on a Riemannian manifold, which also is a complex manifold where the two things are sort of stuck together in some really nice way. Anyway, there's a formula like that, and this is just algebra, and you can just take this algebra. Oh, and this thing also is invariant under kill by the connection. Right? So this is another locally symmetric space, and you can see that from this formula. B, C, D, E equals 0. Right? So it's because all of these things are killed as well. Okay? But what you can do now is plug it into this formula and hope and pray that this is also a flat connection. Right? And it's not. Right? It's not. But it's not too far from being a flat connection. This bit's 0, right, because it's locally symmetric. This bit here is actually relatively straightforward. And you can check that most of the two forms here are killed. Right? So in the sphere, all of the two forms would be annihilated by this algebraic combination. On complex projective space, you can just check that if you take a two form to this combination and see what happens, you find that very few of these things actually contribute to the image here. In other words, the curvature is really trying to be quite flat-ish. Right? And you find that the kernel of this just algebraic mapping is just equal to, at least on the complex level, it's equal to forms of type 0, 2 and forms of type 2, 0 put together. And because of that, you can construct a replacement for the Calabi complex. Right. Okay, so that's what happens on complex projective space. Right, now let me get a bit more carried away. Okay, so the message so far is that complex projective space is a really nice complex manifold. It's a really nice Riemannian manifold. And you can do computations on it, especially by using this formula for the curvature. Okay, but now let me just even relate this construction here, this viewpoint on CPN, to other things that people have thought of over the years. So let's look at the simplest non-trivial case. The simplest non-trivial case is when n is equal to 1, so you're mapping the 3-sphere down to complex projective 1 space. Complex projective 1 space is the Riemann sphere. Right, so somehow in this projection, in this viewpoint on complex projective space, there is this natural fibration as part of your story. The simplest part of your story is a natural fibration from S2 to from S3 to S2, from the 3 sphere to the 2 sphere. This has a name. It's called the Hopf fibration. Right, so it has some nice topological properties. Has some nice differential geometric properties, and so on. Actually, one thing you could do, this suggests a variation on this theme, one thing you could do rather than just modding out by these isometries, which are the action of circle, you could, first of all, you could mod out by antipodal identification. Right, so this nice thing here factors through RP3. So real projective space. To there. Okay, so this thing here is simply another viewpoint on the Hopf fibration. Right. So if you Google Hopf fibration, you'll find all sorts of interesting things about it. Right, so finally, I'd just like to get a bit carried away here and, and see what happens if you replace real numbers here by complex numbers. In fact, if you replace complex numbers here by quaternions. All right, so let's try that. Let's replace real numbers by complex numbers, and simultaneously replace complex numbers by quaternions in this nice vibration that you get here. All right, so what do you get? Well, this is the thing that you're trying to replace. So you get complex projective 3 space, fibering over something. Right, so you get complex projective 3 space, fibering over, so I'll call the fibration pi, fibering over, well, quaternionic projective 1 space. Right, which is a daunting gadget when you first come across it, but just like this one is the 2-sphere, quaternionic projective 1 space is the 4-sphere. Right, so this is actually the 4-sphere. So you get a really nice vibration from CP3 to S4. And it's confusing when you first come across it because the fibers of this are perfectly good complex submanifolds inside CP3. There's no reason for them not to be complex. You might expect if you're fibering a complex manifold by something all of whose fibers are complex, then the quotient is complex. Here is a very nice vibration, which is a counterexample. Hey? H is the quaternions. Yeah, H is the quaternions. But in order to write this down as a mapping from CP3 to S4, you don't really need to know about the quaternions. And one of the exercises in the last exercise sheet is that I've actually written down a formula for this in coordinates. Right? So the formula starts with something here in homogeneous coordinates. I think I've called it psi, because psi1. And I've even allowed myself to write the indices down rather than up. Goes to some complicated formula. And it really is a bit complicated. When you first look at it, you think, that's complicated. But actually, this is where it comes from. Or there are other viewpoints which allow you to think that this would be a good thing to do.
But it is S4 or S3?
No, S4. S4. Right, so this is like S2 for complex, going up by 2 dimensions, S4. Right, so it's H2 modulo, roughly speaking, H2 minus the origin, which is 8-dimensional real manifold, modulo the action of the non-zero quaternions, right? So it's 8 minus 4 equals 4, right? Okay, all right, so there's this. Just by counting, the dimensions of the fibers here should be 2 real dimensional. And I claim that they're intrinsically, they're actually submanifolds, complex submanifolds here. In fact, they're just straight lines. All the fibers are just a particular collection of straight lines inside CP3. Right? They're just, the fibers are CP1s. Fibers are CP1. Right? Embedded inside CP3 in the usual way. There's nothing exciting happening at all. Right? So I'll just tell you why this is such a good thing. And then we'll stop. That'll be it. Right, so the title of this course was Complexes of Differential Operators. At one stage I admitted to you that a good example of such a thing is the Dolbeault complex. Right. Let's look at the Dolbeault complex. Right, the Dolbeault complex is locally exact. Right, there's nothing complicated going on at all. But the Dolbeault complex is not globally exact, even, for example, for a domain. If you've got a domain sitting inside Cn, and even if you just look at so an open subset of Cn, and you ask, you know, what are the forms of type 0p on here, which are Dolbeault closed, d-bar closed, modulo the image, it's not necessarily 0. And in fact, the really, really nice domains are ones for which this is globally exact. Right? So this is locally exact. The nice domains are the ones for which this exact same sequence is globally exact. And they are called, or they turn out to be, domains of holomorphy. So the relationship between the local exactness of something and the global exactness of something, if you have some control over the image of d-bar modulo, the kernel of d-bar modulo, the image of d-bar, in other words, the Dolbeault cohomology, that is telling you something about how you solve problems on D, like the Cousin problem and so on. So all of that can be expressed in terms of this language. But this is all for domains inside Cn. And it turns out that, you know, cohomology there is either it's, you know, finite dimensional, or it's 0, or it's infinite dimensional. And there's, you know, a few little bits of between those two extremes, but not much. Whereas if you have a compact manifold, so some complex manifold, this is compact and complex, and you play the same game for that, then you find that these cohomology groups, which people tend to write like this, right? So if n is the dimension of the manifold, these are available for p all the way up to n. These are all actually finite dimensional vector spaces, and they give you information about this compact complex manifold. So, so these are all finite dimensional. So it's a real big difference between domains and complex manifold, and it's reflected in this cohomology. Okay, now here I'm going to create something by means of this twistor fibration here. I'm going to create something which has a little bit of both in it. It has a little bit of infinite dimensional stuff to it and a little bit of finite dimensional stuff in it, sort of simultaneously. So I just tell you the theorem. So this is a theorem. Roughly speaking, 1976, due to Roger Penrose. There's a few articles around 1976 where this was all worked out. And it says the following. It says that if you take any open subset inside S4, including S4 itself, then if you look at the cohomology of the inverse image, so just look at pi to the minus 1, so pi is my name for this. I look at pi to the minus 1 of u, Right, so that's an open subset sitting inside complex projective space where we're allowed to play with complex analysis now. And you look at the cohomology of this thing. Let's, in particular, the first cohomology, that's the interesting one. And the first cohomology of this, well, if I just take unadulterated sheaf of germs of smooth functions, and nothing terribly exciting happens. But on this space, because it's sitting inside CP3, there are actually a very natural series of line bundles on CP3, which are sort of basics of complex analysis, basics of algebraic geometry. And they are called OK, right? So these are line bundles for k an integer. They're called OK because k is the Chern class, if you like. But I mean, these are very simple to construct on CP3. And in particular, you look at O minus 2. Right, this is the simplest one. Okay, if you look at this, see, one thing you can do is, because I was saying that the fibers of this thing are compact complex manifolds, and in fact they're all just isomorphic to CP1, like that, you can just take this gadget and just see what happens if you just restrict it to a fiber. Right, so you just restrict it to a fiber. That gives you a mapping from this actually infinite dimensional vector space to something else. When you restrict it to a fiber, all the fibers are compact, right? So you just get some finite dimensional vector space. And in fact, H1 of CP1, if you restrict this bundle, right, this turns out to be one-dimensional. Roughly speaking, it's just C. It's not exactly C. There's some sort of little bit of a bundle remnant to it, but it's roughly speaking, it's certainly one-dimensional. So, right, yes, that's another thing. Right, so when people are talking about cohomology like this, once you get used to it, you have in mind a number of different simultaneous viewpoints on this. You can either look at this in terms of check cohomology, which means it looks a lot like sort of topological constructions of cohomology where you have little open patches and so on and so forth, and how things join together over open patches. Or simultaneously, you can think of it as Dolbeault cohomology. I mean, Dolbeault's theorem is that check cohomology is the same as Dolbeault cohomology. I mean, they're canonically isomorphic. Right, so this is a PDE viewpoint, and this is a check viewpoint. And they give the same answer. So when I write something like this, I have in mind actually simultaneously that either of these viewpoints. And I'll come back to that in just a moment. You know, if you like, the best sort of abstract viewpoint is Dolbeault cohomology because it's very clean and so on. But sometimes check cohomology is good. And in this case, even check cohomology is good. So anyway, you can restrict one of these things to each of the fibers and then ask what happens as the fiber varies. Right, so as the fiber varies, you're looking at, well, you're creating something which, strictly speaking, I suppose, is a section of some sort of natural bundle down here. But you can just, in the first instance, you can just think of it as a function on S4. Right, so and what you get is a harmonic function. So you get a mapping from here to the harmonic functions on U. Right, any open set. Right, this is very a little bit surprising. It has nothing to do with the shape of U or anything at all. Right, so so you get something which, as the fiber varies, you can easily check that it's actually harmonic. And rather amazing, this is an isomorphism. Right? Notice that the right-hand side, there's not a complex number in sight. The right-hand side is an open subset of four-dimensional sphere. And actually, you know, the harmonic functions here, the way you're thinking of harmonic functions is actually just by taking the sphere and viewing it with respect to a stereographic projection in a nice conformal patch. Right, so you're actually looking at a function on an open subset of R4. And the claim is that the harmonic functions on that are represented by such a gadget. Right, just to come back to Ahmed's question about whether I'm thinking of this in terms of Čech cohomology or Dolbeault cohomology, it doesn't really matter, but in terms of Čech cohomology, what are you doing? Right, so in terms of Čech cohomology, there's some sort of cover here, some sort of open cover, and you're effecting this transformation by means of some, if you like, some explicit identification of this thing with C. So it actually comes down to doing a contour integral. So there should be a contour integral which is telling you about what's going on here. So some sort of contour integral. You can draw some pictures at this point. They're not terribly helpful, which tells you how to get, you know, in a completely naive way, it tells you how to get from a holomorphic function of 3 variables to a harmonic function of 2 variables. Right, so this u at, say, w, x, y, z is actually equal to some integral here. And I've written down precisely this formula in one of the exercises. And this formula, remarkably, is due to Bateman in 1904. I mean, this is just really ahead of his time. So Henry Bateman in 1904. Right, so if you look at this formula, it is easy to check, and that's one of the exercises, that if you take this thing and you differentiate under the integral sign, the formula here is so arranged that the result is harmonic in these variables. Right? But, you know, what on earth does this right-hand side actually mean? Right? So you can check. But so somehow, you'll notice the rather large time interval between someone writing down a formula like that, 1904, and this actually coming to make really good, rigorous sense in 1976. Right? So there's more than 70 years involved in sorting out this formula. And I should admit at this point that there are other formulae which have not properly been sorted out. I'll just sort of throw that out as an open question. So, for example, you know, this is happening in R4 or C4. It doesn't really matter. This thing here locally, it's in 4 real variables. And if you try and write down a similar formula for a harmonic function of 3 variables, then even the formula looks a bit more complicated. Right? Now, this was done. It was done by Whittaker and Watson. So you probably know that there's a series of classical books by Whittaker and Watson about, well, analysis. And in one of the editions, Whittaker and Watson, the 1922 edition, they write down the similar formula in 3 variables, and then they try and understand what it means. And there's a footnote which goes on for about 5 pages as to what it means. So you can try reading the footnote, and at the end of reading it, you'll be none the wiser, because they didn't know what it means. People were still a little bit mystified by this. And notice in the following edition, after the 1922 edition, the footnote has just completely disappeared. But it's still there if you look in the right library. Right, so I don't know. I mean, it's so this actually goes perfectly well in even dimensions versus odd dimensions. I'll just make have a little rave about the distinction between even dimensions and odd dimensions. So this is to do with harmonic functions. And there's something definitely different going on in even dimensions as opposed to odd dimensions. And you can trace it back to a fundamental difference between all sorts of things that happen in odd versus even dimensions. It generally goes under the name of Huygens principle or whatever. So, for example, the propagation of waves, right? So that's governed by the wave equation. And I'm not sure how many people notice this, but if you take a single line like a whip or something like that, a piece of string, and you do that to it, the impulse that you've applied to that piece of string will just propagate along it on an ideal day with a piece of ideal string, right? So it just goes straight along the string, nothing complicated, right? But if you throw a pebble into a pond, it doesn't do that. You might think that if you throw a pebble into a pond, you'll get this shock wave that just goes straight out from the pebble like this. But that's not what happens. If you throw a pebble into a pond, you'll find these little ripples sort of all interfering with each other as it propagates out. It's not at all sharp like that. Whereas if you come back to 3 dimensions, so you go next dimension up, right, then everything is sharp again. If I send out an impulse to you like this, you hear it as a click. If we were if we were in more dimensions, you wouldn't hear it like that. You'd hear some sort of horrible echoing sound as it came out. So it's a good job that we're having this lecture in 3 dimensions. Otherwise, you'd have to listen to me forever, right? It'd be these echoes coming backwards and forwards that you'd never be able to get rid of. That's Huygens principle, and it's really at the heart of this. And it's also, I don't know, let's just say one more thing about, there's a lot of symmetry going on in the background to this, and in particular, there's the classical groups. If you want to read about the classical groups, it just means the subgroups which are defined by, for example, orthogonal transformations or whatever. You can look in a good book by Hermann Weyl called The Classical Groups. And one of the shocks about the classical groups is that they can be classified. And but the classification, when you first see it, looks a little bit odd. So eventually, people start writing down these mysterious diagrams called Dynkin diagrams. This one here just corresponds to SLNR or SLNC, right? So this is SLN. This is called the A series. Then there's the B series, and the B series is a little bit different. Right? So whatever this diagrammatic notation means, it's actually got some sort of difference at the right-hand end, and the particular difference that it has, this is the B series, is really very different from what happens for the D series. Right, so the D series looks like that, and then there's the C series, which looks like this, where you have to wait until some real explanation of what these things actually mean in order for this to make sense. But this is for the odd dimensional orthogonal groups. This is for the even dimensional orthogonal groups. Right, so this is like SO 2n plus 1. Doesn't matter real or C, it doesn't matter. This is like SO 2n C. They have Dynkin diagrams which look like that. And these things keep on being reflected in life, the universe, and everything, including in Huygens' principle and including in this sort of thing. Right, so I'm getting a bit carried away now. This explicit formula, this one here, is in one of the exercises. Right, I give you the explicit formula. I just ask you to check. I ask you to check that if you differentiate under the integral sign, you get a harmonic function. Right? and then there's something at the end where it says discuss. Right? That's an open-ended question to which I don't necessarily know the answer. Right. Okay. Well, that's nobody minds if you finish 5 minutes early, do they? So I'll stop now.